and to introduce causal cohomology as a main tool for computing minimal resolutions. So let me recall from the last week. So we had the ring of polynomials where K is an algebraically closed field, and one of my favorite examples is C, and we had M finitely generated graded S module, and then there exists a unique up to isomorphism free minimal resolution Fi plus 1 goes to Fi to F1 to F naught to M to 0, where Fi's are direct sum S of minus j to beta ij, and beta ij, since this resolution is unique, give some invariants of the module M and are called the graded Betti numbers. And I'm going to write here on this blackboard, just to keep it for a while. We had the or maybe even better. May I use that one? Okay. So the the Betti table was a table obtained by writing down these numbers in the following way. So here we had beta 0 I, beta 0 I plus 1, beta 0 j. Then we had beta 1 I plus 1, beta 1 I plus 2, beta 1 j plus 1. And here at the end we had beta S, I plus S, and so on. And the reason is that on each row we read linear relations. That was one reason, but we will see at the end of the day that there is a better reason for that. So these numbers actually represent some dimensions of some causal cohomology spaces, and they are labeled accordingly on as we expect. Okay, and we had, given these Betti numbers, we had these quantities bj, which was sum minus I, minus 1 to the I, sorry, sum over I, beta ij, and the Hilbert function of M is written as the sum over j, bj, n plus d minus j choose n, and bj can be obtained from the others. So we take, to obtain a bj, we just take the alternate sum of the elements from the diagonal j. Okay, bj is obtained from the others, like hm of j minus sum k bk n minus j plus k choose n. And I'm going to keep this formula for for a while because we are going to use them. So we see that if on a diagonal there is only one element which is different from 0, then this bj will reduce up to a sign to that element. And if this happens all over the Betti table, then we can compute actually the Betti numbers from the Hilbert function. And we say that in this case, so that's a terminology due to Eisenbad, Farkas, and Schreier. We say that in this case the resolution is natural. So the resolution is natural means that the Betti numbers can be recovered from the Hilbert function. But this is a very rare case. In general, this doesn't happen. Okay. So the last time we discussed the example of 4 points in P2. So for 4 points in P2, so the graded module is the homogeneous coordinate ring of these points, and we have seen that there are 3 possible cases, but we couldn't separate 2 of them just by looking at the Hilbert function. So those cases were, or 3 of them were collinear and 1 was off the line, and respectively they are not collinear. So these cases have the same Hilbert function, but Betti numbers tell the difference. Now, if we look closer to the minimal resolution, which we had, we see that in this case, so the minimal resolution was this one, and to Sx, I'll omit it. I don't write it anymore. And the other one is S of minus 4. S minus 2 to the squared. To the squared goes to S. And what we see, if we look at this map here, well, in the second case, they are just these generators, but they're reversed. In the first case, this map is given by a matrix 3 by 2, and these generators will be the minors 2 by 2 of this matrix. So in both cases, we can write in both cases the generators are maximal minors of the matrix star up to a sign. So the question is this a general phenomenon or not? And this is what we are going to discuss in the first part, points in P2. So if we are given any set of distinct points, in the projective plane, we ask ourselves what can be said about the minimal resolution of S of x, and the answer is given by the following, and this is what is called today as the Hilbert Burch theorem. So it was proved by Hilbert in some particular cases and by Burch in general. So the ideal, the homogeneous ideal of X admits resolution of type. So a very simple type. 0 goes to F, goes to G, goes to IX, goes to 0, where F and G are free modules. So M is a matrix, but we can say even more, such that so the rank of G is the rank of A plus 1. It's exactly like in this case. So the difference of the ranks is precisely 1. And the map G to IX, so the other map, is given up to a sign by the T by T miners of M. So in particular, X is what it's called a determinantal variety. So it's a prototype for determinantal variety. Okay, I'm not going to prove this theorem. Full proof can be found in Eisenbad's book. It's very readable, the proof. I just want to discuss some applications of this theorem. So we know, what do we have here? So we know that whenever we are given a set of distinct points, we can recover the equations from the minimal resolution, from this matrix actually. This matrix will determine everything about our points.
Why we need distinct?
We don't actually, but I just want to avoid any possible problems. Okay, let's discuss a bit more about what kind of invariants can be thrown out of this this resolution. So if we write G as a direct sum S of minus AI is a bit different from the usual notation. So I just want to get some more invariants out of that.
Here T is the length of F.
Sorry?
T by T minor. So T is the length of F or what?
No, not necessarily, because we see here that it's not it can vary.
It's not 2 by 2 matrix?
No, this is 2 by 3.
3 by 2 matrix. So
yes, or 2 by 3, it depends, and this is 1 by 2 or 2 by 1. But the length is the same.
I mean just the T by T. So it's 2 by 3 matrix, 2 by 2 minor, isn't it?
Yes, 2 by 2 minors.
So here T is what?
T is, okay, yeah, T is
length F.
Sorry, yeah, okay. No, I thought the length of X, yeah, sure, thank you very much. So this is T, sure, thank you. Yeah, is the dimension of the matrix. But apparently it has nothing to do with the length of X, can vary, yes, thank you. Okay, so maximal miners. So this is I runs from 1 to t plus 1, and f is direct sum I from 1 to t s of minus bi. So these numbers now ai and bi will represent some invariants of our set of points, and we can order them. Say a1 is the biggest, t plus 1, b1 again is the biggest, and we can consider differences. ei is bi minus ai, and fi is bi minus ai plus 1. So I keep everything, all the notation from Isomad's book, so everything can be found in there. Then, just by from the definition, we get that fi is bigger than ei, but it's also bigger than ei plus 1. And because the resolution is minimal, we would get that fi and ei must be greater than or equal to 1. So, but the difference, if we compare to the other sequences of numbers, the fi's and the ei's are not necessarily increasing or decreasing. They can vary. What do they represent? So if we write the matrix as t plus 1 by t matrix, so the matrix M will be represented in the following way. So if we write the degrees of the entries, we will get here E1, F1, E2, F2, Ft minus 1, Et, Ft in the lower right corner. So this is the matrix. So these are the degrees in the matrix M. And outside we can have well, other differences. So we get a bunch of invariants. AI, BI, FI, EI are invariants of X, and they are not completely independent. So they are related not only by these inequalities, but also by some equalities. So first relation is AI is a sum over j lower than I, EI. We just apply the definition, and we have to make a short manipulation of the relations. Sum of fj, j at least I. So that's one relation. Then of course bi is ai plus ei, and the sum of all bi's is the sum of all ai's. This is from 1 to t, this is from 1 to t plus 1. And moreover, we can recover the degree. The length of x can be recovered from these invariants. So the degree of x is just the sum ei fj. So one first interesting thing is that we can always, so the degree is determined by these numbers. So the proof of this fact just follows from the formula of the Hilbert of the Hilbert function. We just compute the Hilbert function from this formula for the given resolution, and yeah, we find precisely this this fact. Okay. So right from a nice application of this theorem is the following corollary, is that if x lies on a curve of degree d, then I of x can be generated by d plus 1 elements. And this doesn't require any bound on the degree of x. It's just that the fact that x lies on a curve of certain degree. And the proof is very simple. So from this formula we get ai is bigger than t for any I. But then since so x lies on a curve of degree d, it means that there is a form of degree d in the ideal, which implies that there is an I such that ai is lower than or equal to d in the hypothesis. So we get t lower than d, and that's it. Now let's see one example. This is a very interesting example. So points on a conic. So if we assume that our points lie on a conic, then we can write the resolution in a very explicit way. And let's do that. Let's spend some time and do that. So suppose we have the point on an irreducible conic, and d is at least 3. It is one of the. It is the case of 4 points in P2. So the case of 4 points in P2 will be a subcase of this example. Okay. Then d is 2. So from this inequality, we have that t is either 1 or t is 2. So the matrix is either 1 by 2 or 2 by 3, or vice versa. It depends on how we write it. Okay. So, and again, since a t plus 1 is the sum of e i's from 1 to t, these cases will correspond to 1. So let's call this for case 1, and this is case 2. So 1 will correspond to t equals 1, and d1 equals 2. And 2 is the case t equals 2, and d1 equals c2 equals 1. So if we look at the this matrix that determines the minimal resolution, in the first case we will have t equals 1. So we only have 2 by 1 matrix, and this guy here is 2. So we have something of degree 2. And in the second case we have a 3 by 2 matrix, and these 2 guys here are 1. So they are linear forms. In the first case, actually, X is the intersection of the conic with another curve. So the degree of X is even. It's twice the degree of the other curve. And the minimal resolution is like in the first case we have seen the last week. So if this curve is of degree say n, then the minimal resolution is 0 goes to s minus n minus 2, goes to s minus n plus s minus 2, goes to ix, goes to 0. And the Betti table of x will be so we have now we have to distinguish 2 cases, if n is 2 or if n is at least 3. So if n is 2 we have 2 copies of s of minus 2, and here we have s of minus 4. So we recover exactly the case of 4 points which are intersection of 2 conics. So if n is 2, then we get the Betti table is 1, 2, 1. And if n is at least 3, then the Betti table is let's see, 1, 2, 1, 1, and 1 here. So this corresponds to the conic, this corresponds to the other curve, and here we have the trivial relation between the two. But just we should keep in mind this fact that in the first case we get even degree. Let's pass to the second case. So in the second case, the minimal resolution is of type zero, s of minus 1 minus f1 minus f2 plus s of minus 2 minus f2 goes via this matrix to s of minus f1 minus f2, s of minus 1 minus f2. I just replace a's and b's, knowing that e1 is and e2 are 0. Sorry, 1, s of minus 2, and goes to ix goes to 0. So this is the minimal resolution in the second case. Okay, and we had f1 is bigger than e1, which is 1, and f1 is bigger than e2, which is 1. So we get essentially that f1 is at least 1, and f2 is bigger than e2, which is 1. This is what we get from the inequalities. But now, if we apply the Hilbert-Burch theorem, so what does the Hilbert-Burch theorem say? That all the generators are minors of this matrix. We are in the case of a matrix like that, 3 by 2, with these two guys linear forms. But the conic is irreducible from the hypothesis, meaning that these entries cannot be zero, because otherwise, if this one or this one was zero, then we would get a product of linear forms. So all the entries are in this. Let's call this matrix. So we had the matrix M. Let me just copy. Has degrees. One F1 star F2, and the entries of this matrix, which I call M prime, the entries of M prime are non-zero. Yes, because the determinant of M prime is the conic, which is irreducible. Okay, so this also shows that F1 must be 1. And this one also must be 1, just to get a conic. So, and F1 is 1. So we get some extra information. We can replace F1 here by 1. And also from the hypothesis we have A3 is 2. So we will obtain the minimal resolution. Actually looks like 0, s of minus 2 minus f2 to the square. Here we have our matrix A, s of minus 1 minus f2 to the square plus s of minus 2 goes to ix, goes to 0. And again, we have two cases according to different values of f2. So if f2 is 1, then the Betti table is 0, s of minus 2, I'm writing the Betti table directly. So 1, 1, 3, 2. Because we have 3 copies of s of minus 2, and here we have 2 copies of s of minus 3. And the degree in this case of x is 3. So we have actually the configuration is 3 points that lie on a conic, and the ideal is these 3 points are cut by taking another 2 conics passing through them, and these 3 conics will have 2 relations. And the second case is that f2 is at least 2. Then the Betti table is we will have 1, 1. Here we will have 2 copies of this guy, -1, -f2. And we will get 2 relations. So this is the new possibility, and the degree, if we compute the degree in this case, we get, this is 2f2 plus 1. So what do they share in common? The parity is the same, so the degree here is odd. So no matter what, in the second case we get odd degree, and in the first case we get even degree. So in conclusion, if we have an even number of points on a conic, these points will be given by the intersection of that conic with another curve. If we have an odd number of points on a conic, then of course this cannot be a complete intersection, but we would need 2 more generators. So we will have that conic plus 2 more generators of the same degree. That can be conics if the degree is 3, or it can be something of a higher degree if the degree is 5 or more. So in this way we can actually go up to degree 5, at least through any 5 points there is a conic passing through, and get the minimal resolution. And also for higher number of points if these points lie on a conic. Otherwise, if the points do not lie on a conic, we can play the same game, and with some extra work we can say something about the equations. So I hope I convinced you that there is something interesting about Betti numbers. We can prove things actually, like the form of the equations, using just the analysis of these Betti numbers. So since they are interesting objects, we would like to have as many as possible methods to be able to compute these Betti numbers. And the first way is the method involving causal cohomology. So now we pass to a more theoretical stuff. That's the
start on points on cubic.
Sorry?
Smooth cubic. This kind of analysis can be done.
Yeah, it can be done. It can be done. And there is some example. I don't know if it's in this book or in some slides of Eisenbad. If you just Google Eisenbad talk, something like that, there are some slides, and he discusses 9 points in P2.
9 points in P2 on a cubic, or
on 2 cubics and a quartic.
2 cubics and quartic.
Yes, that's an interesting. It's an interesting case.
How about the curves in P3? It's also, can you apply to the Hilbert's Burch theorem?
Yes, yeah, because it holds. Actually, I haven't said that. It holds for codimension 2. So it's codimension 2 that it is essential here. And the next step, codimension 3, was done by Buxbaum and Eisenbad. They have a famous paper on codimension 3. Their paper is actually a generalization of Hilbert Burch codimension 3, or an analog of that. Yes, but it can be done for curves in P3 and it's actually even better. So if you take a general hyperplane section, then the Betty numbers will be preserved. So you can reduce to points in P2 from curves in P3. And this can be seen better if you think of the twisted cubic. So let's discuss this a little bit, because it's a very interesting question. So let's a twisted cubic. What is the minimal resolution of the twisted cubic? So this is in P3. Well, the equations are given by the 2 by 2 minors of the matrix x0, x1, x2, x1, x2, x3. So 2 by 2 minors give equations. This holds actually for any rational normal curve, but you have a longer matrix. And the what are the relations? So we have three quadrics. What are the relations? Well, we just replicate any of the two rows. So if we do that, we get the determinant is 0. So if we expand the determinant by the first row, then we get one relation. And there are two possibilities, where I either add the first row or the second row. So we have two relations given by adding each of the rows and expanding the determinant. So the Betty table looks like 1, 3, 2. Okay. So this is a Betty table of a twisted cubic.
What do you mean, two relations given by adding each row?
Each row?
Yeah, how do you know two relations?
So if you add one row, so x0, x1, x2, x0, x1, x2, and x1, x2, x3, the determinant is 0.
It's 0. So
And you expand. It's
a
a linear relations, yeah. That's why it's on this strand, and not it's linear relations.
How do you know that's all the relation?
You can find it from the Hilbert function, for example. That's the easiest. Let's take the easy way. But anyway, this is identical to this one.
I see.
And these are 3 points. 3 points, 3 general points are a plane section of a twisted cubic. So that's an illustration of this fact, that if you take an irreducible variety and you take a general hyperplane section, then the Betty numbers are preserved. It's probably not clear why, but we will. I hope we will see. So is it okay if I go a little bit over time?
Yes.
Okay. So causal cohomology. Causal cohomology is, in my opinion, the main tool for computing syzygies. And how to get causal cohomology? Let's go back first to the definition, to the origins. The definition of minimal resolution. So what is a minimal resolution? It's a free resolution of this module such that if we mod out M is the irrelevant ideal, so if we mod out M, all the differentials will disappear. So let's look, for example, what happens at this part. So f I plus 1 tensor over s over m goes to fi tensor over s over m. Fi minus 1, the same thing. This is 0, and this is 0. So this guy here, fi tensor s over m, is actually the cohomology of at the middle of this sequence. But the cohomology is something we know. Is the way to get the Tor functors. How do we get a Tor functor? We get a resolution of something and we twist by the other one against which we want to compute the Tor. So this fi, so normally when we compute the Tor we should say that it's the cohomology of the middle, but since the differentials are 0, this is exactly this guy. Is Tor I of m s over m. So if we look now at the graded, these are all graded objects. So in particular, the Tors are also graded. So beta ij is the dimension of the Tor I m s m, the jth graded piece. Okay, this is just the definition of the Tor. But now homological algebra teaches us that we can compute Tor in two different ways. So no matter which module we resolve, we get the same objects because there is some spectral sequence involved. So what we could do instead is to try and resolve this module, S over M. Although it seems a very simple object, it's supported on the empty set, but we can prove things using it. And the minimal resolution of this object is given by causal cohomology. So causal cohomology gives a minimal resolution of S over M, seen again as a finitely generated graded S module. And the result is the following. So let's denote by V the span of the variables. It's actually S1. So the forms of degree 1. Then the minimal resolution of S over M is the following. And I'm just going to write it down. So the tail, starting from the tail, this is wedge n plus 1 V tensor S minus n minus 1. Here somewhere at the middle we have wedge p plus 1 of V tensor S minus p minus 1, wedge p V tensor S minus p, wedge 2 V tensor s minus 2, v tensor s minus 1, s, and s over m. And that's it. Here is just the multiplication map. S of minus 1 stands for the degree. We have to correct the degrees in order to have a multiplication map for the degree 0. But what is this map in general? Let's call dp plus 1. So dp plus 1 is given by, so we apply to a multivector xi0 wedge xip tensor some polynomial p. So what we want to create now, a multivector of length, this is of length p plus 1, we want a multivector of length p. The only way to do it is just to remove the variables, but there is no particular reason to remove just one, so we have to remove all of them one by one. So and we have to sum them up. So I0 wedge. So when I hat here on the position j is that the corresponding element is removed, wedge xip, and now somehow I have to put it back. The only place I can put it back is at the end, so I multiply xij with p, which is consistent because with what's written here, because we want to increase the degree by 1 on the other hand. But we have a little problem, so we want this to be a complex, and if we want that, we have to alternate this sum. So this is the definition. And because of this alternating sign, we get a complex. Now it's not completely obvious that this complex is exact, but in order to prove it's exact, a complex is exact if we can find a homotopy between the identity and the 0, seen as morphisms of complexes. And this is realized by the following. So for exactness, identity and 0 are as a morphism of complexes are homotopically equivalent, and the map is given by the following. So we have this homotopy map, so we would need a map from this element to that one. So if we write two copies of the complex, of the same complex, one on the top and one on the bottom, we would need to have arrows like that on the diagonal. So dp plus 1 should go from wedge p of v tensor s minus p, wedge p plus 1 v tensor s minus p minus 1. Okay, dp plus 1. Again, we apply to one element, x I0, x I p minus 1 this time, tensor p. Now, we would like to increase the length of this multivector and decrease the degree of p. Well, the only way I see to decrease a degree is just by derivation. So we have to take partial derivatives of p, But again, there is no particular reason to take just one, so we have to take them all. So we have to sum dp over dxj, and we just add this xj here at the beginning. xj, xi0, x ip plus 1. And you can prove that up to a sign dp plus 1. So dp plus 1, the dp, sorry, composed by dp plus dp plus 1, composed dp plus 1, is minus p plus d times the identity. Well, maybe one can correct this by d here and slightly modify this dp plus 1, but it's the same. This is on a wedge p v tensor sd. So that proves exactness. So one consequence of this, I'm just going to keep the the original causal complex on the blackboard for a while.
So you need to characteristic zero condition.
Sorry, the
Characteristic zero.
yeah. Sorry, yes. You're right. Yes. Yeah. From now on, I work in. Sure. Thank you very much. So you need in characteristic to work in characteristic 0. Well, I somehow mentioned at the beginning that. Sure. Thank you. Okay. If M now is a graded, a finitely generated S module, we can obtain the Tor functors, the Tors, by twisting this causal complex by M and taking cohomology. So we get a complex. If we twist the causal complex by M, we get a complex wedge I plus 1 V tensor M of minus I minus 1. And let's call this delta, just to distinguish from the other one. Wedge I V M minus I, wedge I minus 1 V tensor M minus I plus 1. The maps are, so this is over K. All the tensor products are over K because these are vector spaces. The maps are exactly the same. It's just that P now is not a polynomial anymore, is an element of M. So, which looks very similar to the original causal complex. So, in particular, Tor I of M and S over M is isomorphic to the kernel of di mod out the image of di plus 1. And in particular, if we look at the graded pieces, if we want to link them to the graded Bettian numbers, then we have to look at one graded piece here, and there is a shift. We have to take it into account. So for any P and Q, we get a similar map, but just on the graded, some graded piece, MQ minus 1, wedge P of V tensor MQ, which p minus 1 v tensor mq plus 1. And the cohomology at the middle, so cohomology at the middle is denoted by kpq of m and v. It's called the causal cohomology of m with values in v. And it coincides, well, mq is the same as m minus p plus q. Because of the definition, it coincides with, so the bottom line is that these Betti numbers, which were Tor ij's, so if we look at the dimension of kpq of mv, this will be precisely beta p plus q. That's because of that shift here. So in particular, if we go back to our original Betti table, we see that here we do have genuine dimensions. I mean, at the intersection of a row I with column j, or vice versa, a column I and row j, we have the dimension of kij. So that's a good justification of writing, another good justification of writing the Betti table the way we did. So in the Betti table, on the position PQ, we get the dimension of KPQ. And another consequence is that Hilbert's syzygy theorem, in all the what we have done so far, we didn't use the Hilbert syzygy theorem. The only thing we used was the existence of a minimal resolution, but we didn't use the finiteness of this minimal resolution. This actually follows, because this is finite. So the tors will vanish from n plus 2 on. All the tors will vanish. So any finitely generated, graded S module has a minimal resolution of length at least n plus 1. And yes, I think I will stop here for today. We continue on Thursday.